So in the last segment, we introduced the classes P and NP. P stands for polynomial time and consists of all problems that have efficient or polynomial time algorithms. NP stands for non-deterministic polynomial time, and it consists of those decision problems for which, when the answer is yes, there is a certificate that we can verify quickly, proving to us that the answer is yes. Basically, again, a decision problem in NP is one where if the answer is yes, there is a solution that can be verified efficiently. Coming up with a solution is hard, but if someone gives it to us, we can verify it. In an NP problem, could we actually compute the solution efficiently rather than just verify it? And we don't know the answer to this. There are lots of problems that are in NP that we would love to solve in real life. They're very important for practical applications. They also have, they have this property that solutions can be verified, but the question of can any of them be solved efficiently is wide open for many decades now. So, and this is the famous P versus NP question. Is P equal to NP? Meaning, if you take all the problems in NP and show that in each case you can actually compute the solution yourself, you don't need to be given it, then you would have shown that every problem in NP is also in P. And that would say that P equal to NP. That would be a major result, probably the biggest open question in computer science right now, is P equal to NP. So how do we go about thinking about this question, and what do we do if P is not equal to NP is going to be the topic of the next couple of segments. So one way to try to attack the P versus NP question is find the hardest problems in NP and try to come up with a polynomial time algorithm for them. Because if you could come up with a polynomial time algorithm for the hardest problems in NP, then you would presumably have polynomial time algorithms for all problems in NP, and you would show that P equal to NP. So if you're going to devote your energy to solving a very difficult problem, you might as well go whole hog and try to solve the hardest problems in NP. Now the only question is, what do we mean by the hardest problems in NP? So, and how do we know which problems are hard? And the key idea for doing this is a technique called reductions, which are very important. They're important here in the discussion of NP, but they're also important in algorithm design. And intuitively, what reductions mean is to take a problem you'd like to solve and you don't know how to solve, and transform it into a problem that you've already solved before. And if you do that, then you can use the solution to the problem you've already solved before to solve the problem that you don't know how to solve. Just to give you a very intuitive example, suppose you're going to a job interview in a new town, and they put you up in a hotel that's kind of far from downtown. And when you're finished with the interview, you need to get to the airport. So you have to figure out how to get from the hotel to the airport. But suppose you've already found out that there is a nice train service from the center of town to the airport. Then, because you know how to solve the problem of getting from the center of town to the airport already, you can reduce the problem of getting from the hotel to the airport to just the problem of getting from the hotel to the center of town. Because if you only get to the center of town from the hotel, then you know how to solve the rest of the problem. So that's a case of a reduction in informal terms. We will see more formal notions soon. What's the definition of reduction? You reduce one problem to another, problem A and B, let's call it. I mean, one problem might be, a problem in computer science is actually an infinite set of possible inputs. For example, a problem A might be, given a graph, does it have a Hamilton cycle? And problem B might be, given a set of numbers, can you partition it into two sets so that they're of equal sum? So these are both problems which take a lot of different inputs. And the reduction says, reduction from problem A to problem B says, given any input for problem A, call it x, the reduction is a mapping that maps x to f of x, which is an input for problem B. So it takes an input for problem A and maps it into an input for problem B. Now, supposing we know how to solve problem B already, that we have an algorithm for problem B, then we can apply that algorithm to f of x. So f of x is the transformed input. So we took x, which is input to A, and created f of x, which is the input to B, input to problem B. Now, if you knew an algorithm for problem B, it gives you an answer, yes or no here, because these are decision problems we're talking about. And the reduction will have the property that whatever answer you get for f of x from algorithm for b will be the same answer that you should get for x for in a, basically. So whatever yes or no answer you get for f of x for b is the correct answer for x for a. So just to give you an example that doesn't quite fit the pattern of decision problems, but it's at least problems you're familiar with. Let's consider the problem A is the problem of finding the median of n elements, and problem B is the problem of sorting n elements. Okay, so again, A is given n elements, find the element that's kind of halfway in rank, meaning the n over 2 smallest element in the n elements. And B is given n elements, just sort them. Now, can you reduce the problem of problem A to problem B? Can you reduce the problem of finding the median to the problem of sorting? Yes, because suppose you have the input n numbers for which you want to find the median. That's the input to A. Your transformation is going to do nothing. It's just going to give the same n numbers to the algorithm for B, which is the sorting problem. And now the algorithm for B is going to sort these n numbers and give you an array of these numbers in sorted order. Now, how do you find the median? Once you have all the numbers in sorted order, it's completely trivial because the median is just the element in the n over 2th position in the array of sorted elements. So again, so the problem of finding the median reduces to the problem of sorting n elements. Let me see, but the other direction is also true. We will talk about that in a minute. But while they illustrate these reductions, this particular reduction is not so good because, in fact, medians can be found faster than sorting. What we've done is we've taken the easier problem of finding the median, it turns out, and reduced it to the more difficult problem of sorting. So if you actually find medians using the algorithm for sorting, you're not doing things as efficiently as you can. It just illustrates the example of reductions. But we can also go the other way. Let's change the roles of A and B, of median finding and sorting. Can we reduce the problem of sorting to the problem of median finding? Meaning, suppose I have an efficient algorithm for finding the median of n numbers. Can I use that algorithm to sort? Well, you can sort of reduce it because to sort n elements, you compute the median using the algorithm for the median finding, and then use the median as the pivot in a quicksort-like algorithm and recurse on the two halves. And the nice thing will happen if you use the median as the pivot is that you'll always partition the numbers into two equal halves. And so the sorting algorithm will be very efficient. Now, this is not strictly a reduction in the sense that I've defined it, because you have to call the median finding algorithm many times in order to solve the sorting problem. Whereas our definition of reduction says you take an input to problem A, transform it into an input to problem B, and call the algorithm for B just that one time on that input. And that's how a reduction is going to work. So this is not strictly a reduction, but I hope you get the idea of using the knowledge of how to solve one problem in order to solve another problem. That's what reductions do. So now we can try to define the hardest problems in NP using the idea of reductions. We have the definition of reductions here. We have a picture for the reductions on the left. And we say that decision problem A reduces to decision problem B if there's a function f mapping inputs of A to inputs of B. So the input of A might be some number x, some input x, and this box is really computing the function, so it should really be labeled f. And out of it comes f of x, which is the input to B. We've seen this before. And what we want the reduction to do is that if x is a yes input for A, meaning if the answer should be yes when the input is x for A, in the problem A, then f of x is a yes input for B as well. And similarly, if x is a no input for A, then f of x is a no input for B. So what that means is that whatever output we get here, yes or no, that we get out of the box for B, the algorithm for B, that same answer is valid for the original question, is x a yes or a no instance of A. We get the output and we can just output that, even though our intent is to solve the problem of x for A. So the reduction is just the function f that's mapping inputs of A to inputs for B. Now, if the reduction can be computed in polynomial time, then it's a polynomial time reduction. Those are the ones that we will study. So basically, we should be able to reduce one problem to another efficiently. Otherwise, there's no point in doing the reduction. So we compute the reduction in polynomial time. That also means that the output produced by the reduction has to be only polynomial in the length of the input. So the input to A and the input to B is not much longer than the input to A. So that's the reduction. And now for the median finding and sorting algorithms, sorting problems, the reductions we gave don't strictly fit the pattern of the definition that I gave for decision problems here, but you can still think about what is f of x, is it computable in polynomial time, and so on for that example. The direction of reducing sorting to median finding does not fit this paradigm at all, because as I said, we invoke the median finding algorithm many times in order to sort. So what does it mean if a problem A can be reduced in polynomial time to a problem B? This means that if B is solvable in polynomial time, then so is A. So again, the picture is you have an input for A, this is x, you apply the reduction to it, and this is a polynomial time reduction f, you get f of x. Then you have an efficient algorithm for B. This is an algorithm for B that also runs in polynomial time. And out it produces yes or no as the answer. And now everything you've done is polynomial. You've taken an input for A, x, mapped it in polynomial time to f of x, produced a string f of x that's not too large, it's only polynomial in the length of x, and then applied the algorithm for B, which also runs in polynomial time. So the whole pipeline is polynomial time, and this whole thing is actually an algorithm for A, if you look at it. So you took this input, and whatever answer you get at the end is the correct answer for x. So if there's a polynomial time reduction from A to B, and B is solvable in polynomial time, then so is A by this picture. That's one implication, and that's very useful in algorithm design. Maybe B is a problem you know how to solve already, A is the new problem you don't know how to solve. Well, you use this pipeline approach if you can, and find a solution to A using the solution to B. And this is something that'll be very useful. So what this is saying is you have the same pipeline, A is reducible to B, again, so X is the input for A, you do the reduction, you produce the input for B, and now we don't know if we have an algorithm for B at this point, so this is an algorithm for B question mark. We don't know if it exists in this case, and it's going to produce a yes/no answer. We don't know if there's an efficient algorithm for B. That's one thing we will figure out now. Now, what you notice is that if we know that A is not solvable in polynomial time, let's say, for some reason, we know that there is no polynomial time algorithm for A. There's no polynomial time algorithm for A, then neither is B going to be solvable in polynomial time. So this is a way of showing that B is hard because we already know that A is hard. Why is that? Well, suppose for contradiction that there is a polynomial time algorithm for B. This algorithm actually exists, this algorithm in this box actually exists and is efficient. Then you can see that we can now have the pipeline that solves A in polynomial time. But we know that's impossible because there's no polynomial time algorithm for A. That means we know that no polynomial time algorithm for B can exist either. So just to give you an example of this kind of thinking from sort of crazy physics, I'm not a physicist, but let me give you this example anyway. Suppose we know that if we could only travel faster than the speed of light, then we could travel back in time. We could go back in time. Okay, so if I could go faster than the speed of light, then I could travel back in time. In the language of reductions, we can say that the problem of traveling back in time or traveling back to the past reduces to the problem of traveling faster than the speed of light. Right? So that's the language of reductions. Now, this has two implications. One is if you manage to travel faster than the speed of light, then we can say, using the fact that using the previous bullet, that now we can go backwards in time. So if you just manage to build a vehicle that travels faster than the speed of light, then you can go backward in time. Conversely, in the same vein, contrapositively to be precise, if we prove that it's impossible to travel back in time, meaning someone shows just there's an absurdity if you're able to travel back in time, so it's impossible to travel back in time, then we would immediately know that it's impossible to build a faster than light vehicle. Okay, because again, this is the reverse implication of a reduction that I mentioned last slide. Let me point out that since I'm not a physicist, I do not know that if the first statement is true or not. That if you're able to travel faster than the speed of light, then you can travel back in time. It's just a hypothetical, but logically, this example is fine. It's just that, so assume that that's true, then all of what I said follows.